Hello, and welcome to Ironbeetle, the show about Tigerbeetle, a pretty excited new database for online transaction processing, which does all kind of like crazy things, like not doing SQL, but also not even doing NoSQL and hard coding the domain model right into the database. Like the crazy database, which doesn't allocate memory after startup, which is written in Zika language, which isn't like, even 1.0. And for the past 50 something episodes, we were trying to make head of tails of like this thing and like why it is written that way, what are like the design considerations, how you could actually and if you could actually build a database that way. But hopefully I've convinced you that this is not vapor there, that this is indeed like, a thing which exists. Okay, so I first of all need to apologize that I've missed, I think, like 2 or 3 past episodes of Ironbeetle. I usually try not to like miss anyone, but yeah, I was traveling for a conference, so I had to miss it. And secondly, I want to apologize for horrific recording quality for the past 2 episodes on YouTube. I'm like, I'm super sad that that happens. Apparently, I've messed up my OBS settings, but hopefully today episode will be recorded with like, the usual, not completely horrible quality. Okay, so let's get started. What do we have on the menu today? On the menu today, we have the grid scrubber. So if you recall, last year when we were discussing state sync, we realized that the state sync is incredibly lazy and that it only syncs the root pointer in the superblock. It doesn't actually go and sync the underlying data, the underlying grid, which is actually okay because our grid assumes that faults can happen. Our grid transparently repairs all the faults from neighboring replicas. So if you imagine a situation where the replica just state synced and the replica doesn't have some grid blocks, it is normal. The replica can continue processing repairs normally, and just that at a point where it will try to read particular grid block from its local grid and the block wouldn't be there, well, the replica will just go and transparently repair it from someone else. But still, you kind of like want to make this thing more proactive. You want to load all the missing blocks immediately. That is like one thing. There is another thing there, and that is, again, Target assumes that the disk can fail, that the data which was recorded once can literally be dropped. So it needs to like somehow proactively check that the data is still good. And for the hot data, for the data which is constantly read and written, this is actually no problem, because, well, we are reading the data, we are constantly verifying the checksum, and the moment something goes wrong, we will repair this data. That's fine. The problem is the cold data, something which we have written to disk a year ago and haven't read since. So it might be slowly be written there, and we kind of like want to periodically poke that. And this is exactly what reliable databases do. They have so-called scribing process, which periodically goes and rereads the entire data set, validating the checksum, just to make sure that no data is corrupted. So let's actually look at what we have here. Okay, so, and there's going to be a couple of moving parts, which I am at this point not entirely sure how they fit together. So we'll have to figure it out. Okay, so let's enumerate the moving parts. First, it is the grid scrubber. This is the thing which will periodically read all the data. Then, inside the grid, we have blocks missing data structure, which actually contains, so like disk scrubber, grid scrubber discovers if we don't have anything, and then blocks missing records the actual blocks which we need to read. They are different because besides grid scrubber, we also have this normal process of reading blocks from disk, which could find corrupt blocks. So both normal transaction processing and grid scrubbing adds to blocks missing. And finally, in the replica, we have on actually, okay, so then in the replica, I think, where is this? I think it should be happening somewhere in the repair, where we want to actually go and request for blocks, but I'm not seeing this. Okay, so let's actually trace everything from the middle. So what I know is that we have what is happening here? I'm lost. Okay, so what we know is that we have like this whole thing should bottom out in these two requests which are sent over the network. A request blocks where a replica says that, hey, I'm missing some blocks, and the block which is a response to request block, the actual block that replica is missing. So let's trace it from the moment we emit the request block requests. Okay, request blocks. Okay, we have send request blocks, and who calls this? Sends request blocks. Okay, yeah, so there is on grid repair message timeout, which is just a normal timeout, which periodically periodically ticks, and yeah, whenever it hits, we send request block. So let's see how that works. Okay, so we get our request message. We slice its body, and then we ask the grid to fill this request with missing blocks, and then we send it to a random replica. Okay, so how does the grid figure out which blocks we need to repair? And by the way, what is a block which we need to repair? Well, okay, this is actually pretty reasonable. To repair a block, we need like a pointer to a block, and a pointer to a block is a checksum and an address. Again, major invariant. Whenever you read data from disk, you should know beforehand the checksum of the data you'll end up reading, because otherwise you won't be able to detect misdirected reads and writes. Okay, so here we see the usage of that grid missing data structure. So, okay, and in this in the set of missing blocks, there are like two reasons for like why we might miss a block. One is that it was triggered by the scrubber or the state sync. So we know that, like, we should have this block on disk. We don't have it, but well, maybe we won't actually need it like immediately or like for the next hour or so. And then the second thing is that we are actually running commit process. We are actually running compaction, or we are running commit, and we need some block right now to process. And for that block, it is high priority. We need to repair it immediately. So this is exactly what next batch of block requests is doing. It first tries to repair blocks which I need immediately, and then like the background thing. Okay. So okay, so these are, I think, the high priority ones. And yeah, the high priority ones are like in the read queue. So this is, yeah, so this like global read queue is the set of reads which are waiting for blocks for repair. So we push into read global queue when we try to read something from disk and the checksum doesn't match. So read let's see this. Global u.push. Okay, so why it is invalid on this code base? Okay, I am. Oh, yeah. Well, this one we've covered, but I am already not understanding how it works. Okay, we read, like we finished reading something from disk, and that something might be good or not. So if the result is valid, we do this. And okay, if the result is invalid, then we push it to read remotes. Okay, yeah. So this is this is the queue of like the blocks which we failed to read, and yeah, we eventually end up pushing this to this read global queue. Okay, so where we were before that. Oh dear, I am completely lost here. Okay, let's go back to the replica. Request blocks. We were in next batch of block requests. Okay. Phew. So okay, yeah, we go through the queue of reads which we must resolve immediately, and we add those reads to this slice of requests. Curiously, like we kind of like actually want to loop over all like everything that's in this queue. So whenever we pop a read, we like add it back to the queue, because like our budget is limited by the amount of requests we can say at a single point in time. So we don't necessarily go through the entirety of the queue in one go. Okay, so if we spend all our budget for read repairs, okay, then that's it. Otherwise, we go to our grid blocks missing. Okay, how does this work? Okay, let's see. What do we actually store in the grid blocks missing? I kind of like took a quick look at this data structure before the stream, and that felt like slightly more complicated than I would have expected. So probably I'm misunderstanding something. So let's kind of like try to understand what's happening here. Okay, so yeah, I guess we are trying to repair. Okay, yeah. So this thing apparently tries to track the entire tables which are missing. That sort of makes sense, probably. Let's see. How do we work with this? What is the public API here? Can I do for okay. Okay, yeah. So apparently we can enqueue either a single faulty block or an entire table. And I think, okay, I will guess that an enqueue table is what is triggered by the state sync, and enqueue block is what is triggered by Scrubber, because state sync operates on the entire tables entirely, because each table is created at a particular checkpoint. Okay, let's check this hypothesis by checking who calls enqueue table. Okay, right, so yeah, okay, that is all right. This is exactly what's happening during the sync. Replica enqueues all the missing tables. Okay, let's see how it works. Sync enqueue tables. So sync enqueue tables, I think, should be happening after the sync, obviously, but I think it also should be triggered after the startup, because if replica crashed and restarted, it might be in the middle of the state sync, so it needs to know what it needs to encode. Okay, let's see. This is triggered by sync content, and sync content is triggered by, yeah, it is triggered by state machine open. So this is the startup. And well, it is sync content done. I'm looking at the sync content. Oh, right, yeah. So it is triggered by the state machine open, but the state machine open itself is triggered when we restart or when we do sync. Because remember, the way sync works is that we pause everything, we cancel everything, we do the sync, and after the sync is done, we go and reopen the state machine again. Okay, so let's see how this thing works. Okay, so the main thing is that we need to know the range of tables we need to sync. Sync of min, sync of max. So sync of min is when we left the cluster, sync of max is when we rejoined the cluster. And like it is kind of acute because remember, due to this repair, replicas might actually continue committing even though they haven't fully synced the underlying data. So it really might be the case that like imagine like this, continuous log for your tables, and you have like a hole in the middle. So you like miss some of the tables in the middle, but you have all the tables before and all the tables after. Okay, so what we do is that okay, yeah, that's exactly it. So we iterate over all the tables we have. And we don't actually enqueue them. So this is just some statistics tracking. Okay. The actual work is in sync and queue tables. And that is I'm still lost here. What is sync tables? Oh, right. Okay, so this is the iterator over tables, which I think we kind of like we sync one table and then we advance the iterator and then sync another table, etc., etc. Okay. So while we have next table to sync, we acquire a table to repair, and we enqueue this table. And if we don't anything else to like repair, like if we run out of budget for repairing our tables, we break. Okay, that sort of makes sense to me. One thing which I don't fully see is what is grid repair tables. So it is a bunch of repair table, and repair table is grid repair table, and that is grid missing repair table, which is, yeah. Okay. No, I don't want settings. Okay, this sort of makes sense to me, although what actually what is now actually confusing to me is like how this well, actually, when we are, so sync and queue tables would not enqueue all tables. Sync reclaim tables. What is sync reclaim tables? Okay, yeah, so when we do repair, we call sync repair tables, which kind of like figures out the tables which we have synced, and then it enqueues syncing all the rest of the tables. Okay, yeah, that makes sense. So, okay, so yeah, it's interesting. So I kind of promised that we are going to talk about the scrubber, but so far we haven't actually got to like the scrubber proper. Okay, so what is puzzling to me is like how this forest iterator actually works, because you see, like, it seems like this is an iterator which is maintained over a long period of time, because like this, like, we sync a table when something else happens, like, we like advance, maybe we like even trigger state sync, and then we like sync tables some more. So this is an iterator over the data, the tables, which, and the set of tables itself is mutated. So, this is like, this, the pattern like which Rust will not allow you to do, like you're iterating over mutable data. So I'm very curious how this works. I think I knew that at one point, but I have forgotten. So let's try to refresh this. First, let's see what is the life cycle of this thing. Okay. So okay, that's actually interesting. This is related to the scrubber. So you see, on the scrubber timeout, if we actually are syncing some tables, then we don't run the scrubber, which makes sense. If you are actively state syncing, that is higher priority than scrubbing. Okay, yeah, and if you've synced the content, then obviously you don't have any sync tables. Okay, if you start sync, you reset sync tables. And in the sync contents, you set them to kind of like default value. Okay. So I guess indeed all the trick is in the next method. Okay, so let's see how it works. Forest table iterator. It is forest table iterator. It is likely it is separate file. Okay, it's actually not that hard, like just 200 lines. Okay, let's see what the comment has to say. Iterate over table info in the forest. The underlying level iterator is stable across manifest log mutation and forest reset open. This is necessary for Scrubber, which is long running. Okay, yeah, precisely. This is what I was curious about. Tables inserted after the iterator starts may be iterated. Tables inserted before the iterator starts will be iterated unless they are removed. Okay, so pseudocode for the iterator. For each level, for each tree, for each table in the level, we yield the table. And a lot of metaprogramming. Okay, so level, tree, and trees. What is a tree iterator? Fields, tree table iterators. Tree table iterator types. Okay, so this one is probably the one which does the real job. Okay, so position is level generation previous. Okay, so this generation trick. Okay, perfect. Okay, yeah. So I get it. So how do we iterate over the structure which is mutated? So we maintain a generation counter. In the structure which we mutate, we increment generation counter every time we mutate. And in our iterator, we also maintain this generation counter. Now, when we want to fetch the next item, if the generation is the same, so if the data structure wasn't actually mutated, then we go and use our physical iterator to iterate. Otherwise, if the data was mutated, then what we do is that we reset our physical iterator, our pointer, by like physically like running the binary search by value. So sort of like, okay, so you have an iterator, you have a sorted array of integers, and you want to iterate all the integers that you're in array at a particular point in time. But the array itself is mutated. Like, you add items to an array, you remove items from the array. So how would you do it? How would you iterate change an array of sorted integers? So, okay, you write a normal iterator, which just maintains an index in the array and, like, yields items from the index. But in addition to index, this iterator also remembers the last value it yielded. So now, if the array wasn't mutated between calls to the iterator, you just increment the index. If the array was mutated, so some value was inserted or some value might deleted, you need in general to shift your index. And this is where you also use the value which you remember. Because what you can do is that you take this value, like the result of a previous call to next, and you binary search it in the newly mutated array. And then you start iterating from the new index. Okay, so this is how forest iterator works. And let me check that there is. Okay, yeah. So this is like previous position, previous. Yeah, this is exactly like the previous yielded value. And where do we say it? Okay. Yeah, so we before we return the table, we save it here. Okay, and the rest is just horrific meta programming for traversing all the different levels and all the different types of our trees. Okay, where we were. I don't want settings. I want sync and queue tables, I think. Okay, yeah. So, yeah, that that is the thing. Is it the thing? That is the thing. Is it? Yeah. When we opened our state machine, we already have our entire manifest log. So we know the whole set of tables. And this means that all the tables we need to sync are in this entire set of tables. So we just go and iterate this entire set of tables. Of course, this set of tables might be mutated, but we do this iterator with sorted array trick to guarantee that we might visit some extra tables, like, the tables which are newly inserted, but we definitely visit all the tables which we need to insert. Okay, so this makes so much sense to me. Okay, so, and then we go and we say, okay, let's add this missing table to our set of missing tables. Okay. Okay, so this is our move table optimization, which we've seen, where we move entire table between levels, which a level iterator might observe. Okay, faulty tables push, and then we enqueue faulty block, which is the index block of this table. And when we enqueue faulty block, I'm curious. What is the side of faulty blocks? Faulty blocks equal. Okay, so that is just kind of like how many concurrent tables we can repair. Okay, that all makes sense. And but what if we can't? Well, we assert that we could, but what if we can't? Can this? Oh, right. And we before we enqueue table, we assert that we haven't enqueued it. Like we haven't exceeded our table budget, and we size the actual queue of missing blocks to have at least one block per table. Okay, that makes sense. So we enqueue faulty block. And this is just the hash table. So if we already okay, this is actually interesting. Could this oh, okay, so this haha, the blocks are actually queued by addresses. So if we already enqueued the block for this address, it must be the same checksum, because I wonder why it is the case. Well, yeah, because if it were a different checksum, then like we are only syncing live tables. Okay, yeah, that makes sense. Okay, so what is progress? What do we do with progress? Okay, so yeah, so apparently after, like, if we enqueue a table for repair, then once we repaired its index block, only at that point we know the values block from this table. So only at that point we can enqueue values blocks. So that's why kind of like we want to kind of like iterate sort of like we do like everything everywhere else, like in compaction or whatever. Okay. And we start with table index. Okay. Okay, well, maybe it makes sense, but I guess that means that at some point, yeah, so at some point, so we could block. At some later point, we will repair this block and we'll get notified that repair was complete. Actually, let's see where are we notified about this. So we are notified by the grid once we have written the block. Okay. And yes, this is the thing. So if what we repaired was the index block we wanted to repair, then we go and enqueue data block here. And I think this is where the bit set comes from. Although I'm not sure. Well, no. Why are you so sure that you actually can enqueue this faulty block? Well, I guess we also size this thing so that it can contain at least oh yeah, right. This is the term. So we ensure that we can enqueue at least like one table worth of data blocks. Okay, so that's why this thing doesn't overflow. And yeah, you see, like this is the static allocation. This is static allocation. You see, like, we add something to data structure, and you immediately ask yourself, hey, what is the upper bound for this data structure? Why we are justified in like doing this? And then you check this upper bound, and this is beautiful. So what you are actually like, this is like type checking. You checked a local property. So like right now, I just manually checked that this particular like append to a queue doesn't overflow. That's like super simple. But because I do these local checks everywhere, I get a really nice emergent property of the system as a whole, that it functions in constant amount of memory, that it doesn't have any kind of runaway loops which can consume unbounded number of resources. Again, this is exactly how Rust safety works, because like in Rust, whenever you call function, you check at the call site that hey, lifetimes are correct. So every individual call site can be checked locally. You don't need global analysis in Rust. You only look at function signatures, and you figure out like, yeah, lifetimes check out. But because you check this at every point, you actually get a global property that the program as a whole is memory safe. That is the same thing with TigerBeetle. The global property is that the program has constant working set. And the way you do it is that at every single expression, you do a local check that, hey, here we aren't actually overflowing anything. And yeah, I mean, the difference is that in Rust, this is done by compiler. In TigerBeetle, this is done like by the combination of like Matplotlib and Whopper, where like, you either look at the code manually and like, reason about like, hey, can it overflow? Can it not overflow? And like a randomized testing, which will find the code being overflow. So it seems like this should be like super error prone, but at least in my experience, we very rarely hit the bugs where we don't allocate enough resources. Like it's not like, surprisingly, this is not hard bug to just not do, as opposed to stuff like not returning pointers to local variables, which every one of us tried to do here or there. Okay. We've finished reading the index table. So we go and we enqueue all the data blocks. Okay. And what was okay? And if this was table data, we just check that we have received this block. Okay, who sets this? Okay, and apparently we set this when we start repairing block. Okay, interesting. So this is, I guess this is just for extra chicken. Yeah, so we first do repair commands that, hey, we are repairing this block, and then we write block, and at the end of write block, we say repair complete. Commands in repair block and repair complete in write block callback. Okay, yeah, that makes total sense to me. Okay, let's go back to our barany. How would you say it in Russian? Okay, so yeah, if we completed the table block, then we check that, hey, this thing is actually received, and that's that was pretty reasonable. Okay, so I think grid mission makes total sense. So it tries to repair a bunch of tables, which bunch is fixed at compile time. So when replica uses grid's block missing, it carefully checks that it actually has oh dear, I'm reading it again on Twitch, and I'm not sure about the etiquette here. Yeah, sorry. I'll just go into carry on, because the purpose here is not Twitch streaming. The purpose here is teaching folks about database. So that is the flow. Grid blocks missing has a certain amount of tables it can repair concurrently, which it is initialized with at any time. And it carefully allocates memory for enough data blocks from all the table blocks. So for each table block, we have one index block and a bunch of data blocks. Okay, so periodically, replica, which is state syncing, talks to grid block missing and asks, hey, grid blocks missing, do you have spare capacity to repeat one more table? If it says yes, it goes and enqueues one more table that needs to get synced, which means that the index block is enqueued. And at a later point, replica goes to grid blocks missing and asks, hey, do I need to ask for any blocks from my peers? At that point, grid block missing said, hey, this is the index block. Please go and fish this index block for me. So replica takes this index block, packs it into request blocks request, and sends it to some other replica. That other replica replies with the index block. Replica receives this index block, writes it to its local grid, and then notifies grid block missing about hey, this block was repaired. And grid block missing is okay, so I wanted to repair this table. I started with the index block. Now I have the index block. This index block contains all the value blocks I need to repair, so let me just enqueue all those value blocks to the statically allocated queue I have for them. And then once all the blocks are repaired, the table should be popped from the queue. And this actually, I think we haven't seen. Okay, so somewhere we should check. Yeah. So here we check that we've repaired all the data blocks, and that means that we actually free up the space in faulty tables. So when replica then replica asks about whether we have. Oh, okay. So haha, there's one more step here. So let me not go to the settings. Let me go back. Okay, so we basically push this to queue of 3 tables. Then replica calls sync reclaim tables. Which goes to this free list, pops a table, and then that table is added back to the replicas queue of 3 tables. And then if we have like more tables available, then we request another table to get sync by the grid blocks missing. Okay, so that's interesting. So I wanted to talk about grid scrubber. Grid scrubber. I ended up not talking about grid scrubber and instead finishing our sync discussion. But I'm not sure about you, but at least for me, I now understand how everything is, how everything fits together. Okay, so let's maybe okay. I want to do a short recap, but I realized that I have no idea what is this thing. So let's, and that sounds like important. So let's see what it might be doing. Checkpoint durable commands. So it might be actually pretty new code. Okay. Okay. Yeah. So I get what it means. So we are repairing tables, but of course data is mutable. So while we are repairing the tables, actually the tables might get deleted, which happens at the checkpoint. And at that point, like, if a table is deleted, its data might be reused for other things. And we, if it is reused, we shouldn't be repairing it because we'll be clobbering newer data. So then the thing happens when we flip over the checkpoint, we go and see if any of the blocks we are repairing are now free, and if they are, we actually say, okay, we just stop repairing this because that is not necessary. Okay, yeah, I think I now understand everything. So let's see how this entire sync of the actual data works. Okay, stop. State sync in a nutshell. Replica goes about its own business, and then it realizes that it is far behind the cluster, that the cluster is on some future checkpoint. Replica says, okay, no problem. I'm not going to try to catch up with all of you by replaying the log, because it might be the case that some messages in the log are no longer available in the cluster because the cluster moved ahead. So I'm going to jump directly to your state. The state, because everything on disk is a persistent SN functional data structure, is actually can be compressed into a single hash, into a single checksum of the root superblock. So when the replica state syncs, it actually just syncs this root pointer. So after the state sync, replica has a superblock which contains the latest state, and it knows which ops it jumped over. So for example, if replica started state sync at op like 100 and the cluster was and synced to a checkpoint which is at op 10,000, then everything behind 1000 and 10,000 needs to be state sync. We don't necessarily have this data. So this is the state of the replica after it restarts after the state sync. It has a bunch of ops for which the data might not be there. So what the replica does next is that it iterates over all the tables it has, and for every table which was created between those two boundaries, it enqueues this table into the grid blocks missing, which triggers this repair procedure where we first repair the index block and then we repair the values blocks. So far, so good. The problem here is that the set of things we want to repair isn't actually immutable. Some table which was created during our interval might be deleted later. So like iterating over this set of tables is actually pretty hard. Kind of, I mean, what we can do is that at the start, we can just copy all those tables from the manifest into some separate allocation, but that means like, doubling the memory for the manifest. So we kind of like do this like crazy thing where we iterate over immutable data structure. And the way we do it is that we, normally in the iterator, you remember like just one thing, which is an index. For our iterator, we remember three things. We remember the index, the generation of the underlying data structure, and the last value we yielded. So on our iteration, first thing we do is that we check the generation. If the generation is the same, that means the data structure wasn't mutated in the meantime, and that means that we can just reuse the existing index and just do +1. On the other hand, if the generation is different, that means that the data structure was mutated, and that means that our index is not necessarily correct. So we must refresh our index. But because we remember the previous value which we yielded, we can just binary search for the correct index in the updated data structure and update our generation. So yeah, that's basically it. Of course, we cannot, repair everything all at once. That's why we have a certain statically sized limit on the number of tables we are repairing concurrently, and we do this like delicate dance where we enqueue as much tables as we can, and whenever one table is fully repaired, we go and repair the next table. One thing I want to understand though is like how we update op repair min and op repair max. Because I mean, what you can do is that you can, after the sync, say, hey, there's a whole bunch of tables I need to sync, and then which is stored in your superblock, and you clear out that information once you fully finished the state sync. But that means that you cannot crash while you are syncing the data. So I think at some point we should be storing intermediate progress. And sync. Okay, I think this is sync min old. Okay. Okay, checkpoint superblock. So this is where this should be happening. So we actually it seems like we actually don't do this. We just say, okay, so if we are fully done, then we don't have to sync anything, and if we are not fully done, then we just do everything, and like presumably the next time we'll have to start from scratch, which is yeah, look at yeah, like I mean, if we did repair this data, we won't be requesting them over the network. I think we'll first try to read them locally, and if they're there, we'll just say, okay, no need to repair this. Okay, so I guess that's it for today. As I've said, we've topically we should have looked at the scribing process, but instead we actually were finishing parts of the thing. But I mean, it's not exactly that, because like we've looked at this core piece of infrastructure with grid blocks missing data structure, and this is exactly the thing which the scrubber is going to use to track the data that was scrapped and found faulty. And by the way, we've also looked at the stable force iterator, and that is also something which is reused by the scrubber, because, well, scrubbing and syncing are actually pretty similar processes in there. Okay, thanks you for listening. Again, sorry for missing couple of past episodes, and sorry for horrible YouTube quality, but hopefully it should be better from this point on. So every Thursday at 5 p.m. UTC, you can join me live on Twitch, where we'll continue our study of Tagabidal. And if you miss it, you can always watch a recording in hopefully a relatively good quality on YouTube. Again, thank you for joining, thank you for listening, thank you for rating, and goodbye. See you in a week.